Hello dear students, welcome to chemistry classes. So this is a NEET previous year problem solving series. So in this session or in this video, we are going to solve some problems. Okay. So here, let's see first one. The vacant space in BCC unit cell is the vacant space present in the BCC unit cell. It is the simplest question asked in NEET. Okay. So please solve this question on your own. And I will give the hint how to solve this. So here we know packing efficiency. Packing efficiency means what? The amount of space, the amount of space filled by the particles in an unit cell is called as packing efficiency. And they are asking the vacant space. Vacant space means what? The amount of space, the amount of space remain vacant in the unit cell. So the total space of the unit cell is taken as 100%. So if some percent of unit cell is filled, the 100 minus that, the remaining will be vacant only. So please solve this question on your own and send me the answer in my comment box. Okay. So don't miss this. Next the second question. The correct statement regarding defect in crystalline solid is. The correct statement regarding defect in crystalline defect in the solid. So option A. Frankel defect decreases the density of solid. So first let us know about Frankel defect and Schottky defect. Here they have discussed only about Schottky and Frankel defect. So in Frankel defect what happens? Frankel defect here. See here, if this is our ionic solid, then what happens here in case of Frankel defect? So basically Frankel defect is a dislocation defect. Frankel defect is a dislocation defect. Why? Because in Frankel defect what happens? The small sized cations leaves its own space, its own site, and will occupy the interstitial site. Here this is the own site of the cation. It leaves this own site and it will occupy the interstitial site. So what happens? The number of ions remains same. So as the number of ions in the crystal remains same, there is no change in the density of the crystal during Frankel defect. So Frankel defect means basically it is a vacancy defect in its own position and interstitial defect on its new position. Okay, the small sized cation leaves its own space, remain vacant, and it will occupy the interstitial site. So the location of the ion just changed. So this is basically a dislocation defect. During this what happens? During this defect, the density of the crystal system remains same, and such type of defect is observed in the crystal like zinc sulfide, silver chloride, silver bromide, silver iodide, like that. Especially this type of defect is observed in the crystals in which the size of the cation is small and size of anion is larger. Means there must be a large difference between the size of anion and the cation. In such compounds you can observe this defect, Frankel defect. In other hand, what is Schottky defect? In Schottky defect what happens? Equal number of cations and anions removed from the crystal. So as equal number of cation and anions removed, the crystal remain electrically neutral and density of the crystal decreases, isn't it? And this Schottky defect, as number of ions are decreased, due to that in Schottky defect density of the crystal decreases. Okay, so let us see. Frankel defect decrease in the density of the solid. So this is wrong. During Frankel defect density remains same. In Schottky defect density decreases. So this is not our answer. In Frankel defect, the Frankel defect is a dislocation defect. Yes, the Frankel defect is a dislocation defect. We got the answer, but however, let us see two more options. Why? Because some questions are asked. In those questions, more than one answer may be correct. So in such condition, Frankel defect found in halides of alkaline metals. See here, the Frankel defect is found in the halides of silver and is also found in zinc sulfide, isn't it? So we cannot see the Frankel defect in halides of alkaline metals. So this is also wrong. In Schottky defect, Schottky defect have no effect on density. So what happens during Schottky defect? Density of the crystal decreases. So this is also wrong. Option B is my correct answer. Okay. So like this we have to solve the problem. First we have to read the options, given options correctly, then we can solve. Okay. Next, and these two questions are asked in NEET 2015, and this question is also asked in NEET 2015. But this NEET exam was cancelled initially, and afterwards they will conduct another exam. In those exams these questions were asked. So, and however we will solve this problem. A given metal crystallizes with a cubic structure. A given metal crystallizes with cubic structure. We don't know which cube it is. Having edge length of 361 picometer. So what's given here? Edge length A is equals to 361 picometer. They have given edge length 361 picometer. If there are 4 metal atoms in one unit cell, yes, this is our hint. If there are 4 metal atoms in one unit cell, number of metal atoms in unit cell is equals to Z is equals to 4. If number of particles in one unit cell is equals to 1, it may be SCC, simple cubic lattice. If the number of particles are 2, it is BCC. If the number of particles are 4, it must be FCC. So the given compound, the given cube is FCC, isn't it? So this is our hint, FCC. There are 4 metal atoms in our one unit cell. What is the radius of one atom? They are asking for the radius of one atom. So by using this relation, by using the value of A and FCC unit cell, we have to calculate the radius of the metal atom, and just we have to establish relationship between radius and edge length. So let's see how to derive that. So I will consider, for the sake of simplicity, I will consider only one face of the unit cell. Actually this is our entire unit cell. In this unit cell, I am going to consider only one face. Here, I will consider only this face. So this is face diagonal. I'll take it as B, and the side of the cube is nothing but edge length. So edge length is taken as A. Let us take this is A, B, C. And we know that in FCC unit cell, there are the particles present at the corner, and also the particles are present at the center of each faces, isn't it? The particles are present at all the corners of the unit cell, and also the particles are present at the center of each face. So in that condition what happens? Let us derive the relationship. Let us take a radius of the particle as R and R. Okay, and by applying Pythagoras relation, we have to calculate the length of B. So let us take in this triangle ABC, in triangle ABC. So we don't have more time in the examination, so we have to solve this very much shortly. If we don't know the relationship between radius and the edge length, we have to we'll try to derive the relationship. In the triangle ABC, what happens? AC square is equals to AB square plus BC square, and we know AB is equals to A square plus BC is equals to also A square, means B square is equals to 2A square. What is B? B is equals to root 2A, is equals to root 2A, and from this figure we can write directly that B is equals to what? R plus R plus R plus R, 4R. So this is B is equals to root 2A, B is equals to 4R. We can equate them. What we can get? 4R is equals to root 2A, isn't it? So from this we can establish the relationship between radius of a particle and edge length. So R is equals to what happens? Root 2A divided by 4. What we can write? Root 2A divided by 4 as can be written as root 2 into root 2 into 2. Root 2 into root 2 means 2, 2 into 2, 4. So what happens here? 2 cancels out. What remains? A divided by 2 root 2. So therefore R is equals to A divided by 2 root 2. This is my relationship. By using this relationship, I have to solve the problem. Okay. So now I don't know R. I have to calculate R. R is equals to A. A means how much? 361 picometer divided by 2 into root 2. So what is the value of root 2? Root 2 is equals to 1.414, isn't it? So root 2 into 2. What happens here? 361 picometer. What is the value of root 2 into 2? It will be 2.828, isn't it? On multiplying this with 2, what happens here? 2 into 1, 2, 2 into 4, 8. Yes, like this. 2.828. I'll directly write it. So we can write 2.828. We can write it as 3 for the simplification. For the simpleness of this problem, we have to take 2.8 as 3. If I take 2.8 as 3, then it becomes very much easy to divide. Otherwise, it becomes lengthy. Okay. So, however, I am going to get a near answer, not exact answer. Based on that near answer, I can guess the options. So, here I will divide 361 divided by 3. Here 361 can directly take 120. 123 is a 360. So 0 0 1 remains. Here 9 and 1. Okay. So 120.3. R is equals to how much it is? 120.3. Let us see the options. Oh, sorry, I forgot to write the options. Wait, I will write the options. So here option A is 80 picometer, option B is 108 picometer, and my option C is 40 picometer. Option D is 127 picometer. Let us see the options. Which one is near to our answer? Our answer is 120.3 picometer. Here picometer, 120.3 picometer. This is near to which option D? So this is our answer. Okay. So like this we have to solve the problems. If I take 2.8, it becomes very much difficult to divide. So in that condition, what happens? We are wasting the time, but we are not getting the solution early. So for that we have to take these approximations. Okay, like this we have to solve the problems. I hope this is we have understood this, and please don't forget to give the answer in my comment box. Okay, thank you so much for watching.